Good morning, everyone. Welcome to Chemistry 2423, Section 20005, also known as Organic Chemistry 1. My name is Dr. Fong No, and I'll be your professor for this session, this summer session, which is very short. The course is only 5 weeks long, and so we'll be going through this very quickly. We don't return to campus at TCC until the fall, so the entire course will be taught online. So I'll be your professor for both lecture and lab online. We'll talk a little bit more about lab in a little bit, but just a little bit about myself before we get started with the syllabus and our very first lecture. So again, my name is Dr. Fong No, and I recently began teaching full-time. Before that, I was actually a forensic scientist at the Dallas County Crime Lab, and before that, I was a forensic scientist at the State Crime Lab in Alabama. I got my education at Sam Houston State University, a PhD in chemistry at Auburn University, and so that's where I am now. So I think I'm kind of qualified to teach the class. Anyway, so a little bit about this particular this summer session of Organic Chemistry 1. Like I already alluded to before, it's going to go by very quickly. We have a lot of material to cover and only a month to cover it, or a little bit over a month to cover it. And what that means then is that we're going to go through this stuff very, very fast. We're talking like a chapter a day. Sometimes the chapters are kind of long, and so they'll go maybe a chapter and a half, or they'll go a day and a half for a chapter. We'll also have an exam every Friday until the end of the session. And just to make sure you're keeping up with all your work and what you're learning throughout the month, there will be assignments and quizzes that are going to be due sporadically throughout the semester. You'll see it on the schedule in Blackboard. So that being said, bringing me to Blackboard, everything in the class will be distributed either through Blackboard or LabFlow. So Blackboard will have all the lecture materials and all the handouts and all that stuff, including this video lecture. And all the rest of the video lectures I'll be doing for the rest of the semester or the rest of the summer session. And then your labs will be done completely online using LabFlow. And it's a completely different website, different portal, and there'll be instructions in the handout section on Blackboard for you to be able to sign up for a LabFlow account if you haven't done so already. If you've done a previous lab here before during COVID times, then you've probably done LabFlow already, and it's pretty simple. But there'll be a little primer to prep you for how to do an organic lab in LabFlow. So before I go any further, let's go ahead and talk about the syllabus and how the class is going to be structured, since it's a summer session and it's also completely online. And as you know, teaching chemistry online is not easy, but we'll do the best we can with what we have. And hopefully everything will return back to normal soon, and we'll be back on campus in the fall. So let me change the view here real quick so that we can take a look at the syllabus. There we go. So when you log into Blackboard, you should see our section, which is 20005, on your My Courses box right here. And so I'll click on that, and I don't have any announcements in there yet, but there will be a lot of announcements, so make sure you pay attention to those announcements, right? But if you look on the left-hand side here, there's announcements, syllabi, course schedule, important handouts, lecture videos, assignments, quizzes, and exams. There may be a few more, links in there I'll put in throughout the session if I feel like I need to, but the vast majority of the things that you'll be doing will be in those sections. So let's quickly take a look at the syllabi. We have the lecture syllabi here, and we have the lab syllabi. We'll go through the lab syllabi in a different video, because I'll have another video just to prime you or prep you for as a primer for using LabFlow as your laboratory assignments and your laboratory assessments and stuff. So we'll click on lecture syllabus first, and this is how it pops up. Just give it a second here. You can do it. There it goes. And this is the syllabus for our section. So let me see if I can make this bigger for you to see. I'm actually going to just open it completely here. There we go. And then we can take a look at it through here now. Okay, so basically this is a course based on carbon chemistry. So organic chemistry is about carbon chemistry, right? And you can see here we're talking a lot about the structure, the bonding, the properties, and the relative, the reactivity of organic molecules. And organic molecules are molecules that contain chemistry. We assume that you have already mastered general chemistry, and so there will be very little review to help you be caught up with what you need to know from general chemistry to be able to be successful in organic chemistry. So let's scroll down a little bit. The textbook that you'll need is the Organic Chemistry 4th edition by David Klein. It's a very helpful textbook. When I was an undergrad, which was not too long ago, I had you're already at the 4th edition here, but I had the 1st edition. And I felt like the 1st edition of David Klein's book was the best organic chemistry book ever written. It's written more like a story, and it relates really well to real world applications. And I feel like that's the best way for me to learn, if I can relate it to real world applications. And I will do my best to do it for you. I can't guarantee the success of that, since we're going to be going really fast, and we have a lot of material to cover in a month. But we'll see how it goes. But as you can see on my bookshelf back here, I have multiple organic chemistry books right here. See, right there, right there, right there. In fact, I think that when I was in undergrad, McMurray and Wade were the 2 books that we were supposed to be using, but I still used my David Klein book more. So be lucky that you're actually required to have the David Klein book and no other book. Feel lucky about that. So what are the required materials for the course? You'll need a computer, of course, right, with a webcam and internet access so that you can access Blackboard, LabFlow, and Wiley+. So when you buy your textbook, you'll be able to get access to Wiley+. And on Wiley+, there'll be supplemental videos that will help you work through the problems that I'll be assigning, or practice problems and things like that. So make sure you're able to get a hold of those things. It's not absolutely required. You don't need to do it. Nothing in Wiley+ is absolutely required, but it is super helpful to use Wiley+ because there's a lot of videos in there and a lot of practice in there for organic chemistry material. And we'll take a look at it in a second. So you also need Microsoft Office, which is available for free for students. That's for you to be able to write your reports and stuff in lab and that kind of thing. And you also need Adobe Acrobat, which is pretty self-explanatory. All of our handouts and stuff will come through PDF form, which is going to be read by Adobe Acrobat. Some class requirements here. This is just generic stuff here about privacy and computer stuff and the remote proctoring service for you to be able to do your exams online at home, and then also be able to access things on Blackboard and LabFlow and Wiley+. We'll talk more about the remote proctoring in a second. My apologies for the interruption. We're all working from home, and at the time I'm recording this lecture, it is actually storming outside, and the power just went out. So again, I apologize for that interruption, but let's continue on. So let's go ahead and talk about the grading criteria then. The course is divided into 2 parts, the lecture and the lab. The lecture is worth 75% of the grade, and the lab is worth 25% of the grade. And then the lecture grade is broken down as follows. You have your daily assignments, quizzes, and online participation. All that is worth 10%. The lowest of those will be dropped. The lecture exams will also be included, 40% of the 75%, and the lowest lecture exam grade will be dropped. And then you have the final exam, which is worth 25% of the entire lecture grade. The final exam will not be dropped, so it is absolutely imperative that you take the lecture exam, the lecture final exam, sorry, because the final exam will not be dropped. So lastly, we have the laboratory. It's worth 25% of the grade, and we'll talk more about that when we go into the pre-lab lecture video. So Next, we have the grading scale. It's pretty self-explanatory on how you get an A, B, C, D, or an F in the class. You can look at that yourselves. And then we move on to the online structure of the class. Generally, chemistry classes are taught face-to-face, so it's a particularly difficult challenge to teach organic chemistry, worst of all, online. But we'll do the best we can with what we have. So lectures then will consist of video lectures like the one that you're watching now. They'll be generally 60 to 90 minutes long, and they'll be posted every single day at 8 a.m. Of the class, except for on lecture exam days. So, as I was telling you before, at the very beginning of all this, we're in a summer session. The course is only 5 weeks long. We have a lot of material to cover, and I'm going to do my best to adhere to the schedule that I've put out on the on Blackboard of the topics that we're going to cover. And some of these topics might exceed or might be less than 60 minutes or even 90 minutes. I know for a fact that my attention span starts to wane after about 50 minutes, 50 minutes. So I'm going to try to keep them all to about 60 minutes and have it where if we don't finish a topic or a chapter, we'll go to the next day with that chapter. But the problem with that is that it pushes things off and makes us way behind, and you won't be prepared for organic chemistry 2. So, though I'll do my best to keep us on schedule, we might go past 60 minutes and go to 90 minutes on some lectures that are a little bit more long and involved. But we'll do the best that we can. So, the vast majority of the material that you'll be using you'll be learning for the exams and the quizzes and the assignments will be distributed in the video lectures. The book can be used as a guide. In fact, most of the lecture comes from the textbook. So you can definitely use it to supplement what you're learning in lecture, in the lecture videos, and I definitely think you should do that. But the vast majority of the things, 99% of the things that you need to know for an exam, quiz, or assignment will be conveyed to you during a video lecture. So again, these are posted every day of class except for exam days by 8 a.m. and they'll be available for the duration of the class, except for during quizzes and exams. So I recommend then that you take notes, very good notes, during the duration of watching a lecture video, and have the textbook next to you to clear up things that may not have been as clear from the lecture video. But then we also have the Wiley Plus resource, and as we go through different lectures, I'll tell you Wiley Plus has a video that explains this even more if you need it, and you can go into Wiley Plus to take a look at the video or any other resources Wiley Plus has. And you get access to that from the textbook, as I said before. We'll take a look at Wiley Plus after I get done with the syllabus. Next, we have the quiz, the quizzes. The quizzes will be there will be a quiz for every day of the class, except for the first day, which is today, and then days that are a day after a lecture exam. There won't be a quiz. And the quizzes are meant to make sure that you're keeping up with the material that we're being taught. Make sure you're doing your due diligence in watching these videos every single day, taking good notes, and using the additional resources like your textbook and Wiley Plus to make sure you master these things and do well on your quiz. Because if you don't do well on your quiz, then you have an indication of how things will go on your exams, right? So the quizzes are generally 10 to 20 questions long. You have 15 or 30 minutes to take them, depending on how long the quiz is, and they'll be posted at the exact same time that the lecture exam is posted, right? So 8 a.m. Not the lecture exam, I'm sorry, the lecture video is posted. So at 8 a.m. and you have 24 hours to take the quiz. That means if it's posted at 8 a.m., you have 8 till 8 a.m. the next day, or 7:59 a.m. the next day to complete that quiz, and that's what it's due. You can have only one chance to take the quiz. Once you've entered the quiz, you cannot leave the quiz, you cannot redo the quiz, you can't do anything like that. You only have one chance to take the quiz. But on quizzes, you are allowed to use your notes and your textbook. So that's why I'm telling you that it's probably a good idea that you have your textbook and your notes handy, having taken really good notes from the previous day, right? You do have that option, but you only have one chance to take the quiz. It's either 15 or 30 minutes long based on the length of the quiz, and it is open note, open book, right? And you have 24 hours to complete the quiz every day, other than the first day, which is today, and on exam days. So next, we have our lecture assignments, and lecture assignments are different from quizzes because we only have lecture assignments assigned after a chapter is complete. So, for example, the first chapter is a review of general chemistry, just to make sure you're up to date with everything, and that you were supposed to learn last year, in general chemistry. And I already know for a fact that this will take me 2 days at least to do, right? And so that means then you won't have an assignment actually posted or assigned for the first day of lecture, but when we finish the chapter, which will be the second day of lecture, you will have one of those assigned, okay? Again, these will be posted the exact same time as the lecture videos, and you can actually, if you wanted to, watch a lecture video and do the assignment at the same time, right? The only difference between a quiz and a lecture assignment, that a Blackboard assignment that's going to be assigned at the end of every chapter, is that both have a 24-hour duration that you can max limit that you can actually complete the quiz, but the difference is that you have unlimited attempts to do the assignment. And of course, it's open book, open notes, and all that stuff, right? So that's the difference between a quiz and an assignment. An assignment, you have multiple chances to take it. So I recommend that you take it as many times as you need to bump up that grade, to bump up your final average, right? There'll be, there could be anywhere from 20 to 30, 10 questions long. It depends on how much material is covered in that particular chapter, or it could be a discussion question, or it could be a supplemental video response or something like that. But most likely, since it's such a fast semester, things are going by so quickly, there'll probably just be multiple choice questions on Blackboard assignments, right? So remember, 24 hours from the day that it's posted. So if it's posted at 8 a.m. one day, the next day by 7:59 a.m. it will be due. And assignments you have multiple chances to do assignments, right? And they are open book, open note. Quizzes, on the other hand, everything is the same except you only have one chance to take a quiz, not multiple. Okay? Then we have our lecture exams. So we have 4 lecture exams throughout the semester. You'll see that on the schedule. And they're going to be at the end of every week, right? And so, for example, this week we're going over general chemistry review and molecular representations. So what that means then is that on Friday you'll have an exam over those things, okay? Exams are taken online at home, in the comfort of your own home, on your own personal computer. They're posted at 8 a.m. and they're due by the end of the day that day. So 11:59 p.m. that same day. You must complete the exam the same day, right? Generally, they'll have 25 questions or so, and you'll have 60 minutes to complete the exam. Now, if this is the first time you've ever taken an online class at Tarrant County College, you may not be familiar with this, but whenever we do online exams that are done at home, they're remotely proctored by a third-party company called Proctorio. Proctorio will require that you have Google Chrome as your browser, and have a working webcam so that you can be monitored and proctored remotely. And so that's what we do to ensure academic integrity while you're taking your test at home. So just to briefly go over these bullet points here, and you can look more deeply into them, as we get closer to an exam, which will be on Friday. You will be monitored by Proctorio for exams. You must complete the exam in one sitting. You'll need to have a webcam and a microphone connected to your computer for the exams. We do that so that we can see see you as you're taking your exam and hear if you're getting any kind of input, while you're taking the exam, that kind of thing. You also need to have your ID for verification. So what you need to do there is just have you and your picture ID and show it to the webcam at the very beginning when you're right before you're about to take the test. Okay. So during the exam, and Proctorio will not allow you to do any of these things, because if you do any of these things, it will just kick you out and you end up getting a 0 on the exam. Okay. You're not allowed to open any other browser windows. You cannot access their textbook. You cannot take any photographs, screenshots, or print any portion of the exam, or visit any other websites during the exam. Okay, and just believe me when I say that if you violate any of these, Proctorio will kick you out automatically of the exam, and you will get a 0 on the exam. As you can see by this next statement here, failure to comply with any of these guidelines or any violations therein will result in an immediate 0 issued for the grade for the exam. All right? And of course, I understand that there can be technical issues with anything, and I will do my best if you have a technical issue to try to rectify the issue. But I will tell you that if you get kicked out of the exam, there is absolutely no way that I'm able to put you back into the exam for you to continue the exam. Okay? I don't anticipate you'll be needing a calculator for this class, but if you do, you are allowed to use a TI-30 calculator or any non-graphing calculator on the exam. And you can actually do scratch work if you need to do scratch work on a piece of paper that you show to the camera that is blank during the exam, right? Or on the digital whiteboard that's also provided during the exam from Proctorio. I do have office hours. And those office hours are Tuesday, Thursday. Whoops, sorry about that. Let me maximize that again. There we go. I do have office hours. And those office hours are Tuesday, Thursday, 4 p.m. to 5 p.m. And since we are all online, we are doing office hours in Microsoft Teams. Everybody has access to Teams because as a student you have access to a free copy of Microsoft Office, and Teams is in that. And if not, you can just download Microsoft Teams because it's free in general. And what happens is that you've already been added as a member of our team. This section, the Organic Chemistry 1 CHEM 2423-20005 section team on Microsoft Teams. And I will be there, present there, for us to chat every Tuesday and Thursday from 4 p.m. to 5 p.m. for office hours. But if you can't make those office hours, feel free to email me at my email address right there. And we can set up another time where we can meet on Teams. We're not on campus yet, so my phone number, you can call me at my phone number, my office phone number, but I won't be there. The best way to contact me is through email. And then lastly, we have our schedule here. And it's the same thing that's actually posted on Blackboard in the schedule section of Blackboard, but I'm going to switch it over there because it's easier to see things over there. So let's go to Blackboard and press this little blue thing here to open up the menu, and we can go to course schedule. And it's kind of small, so let's see if I can zoom in just a tad here. I just love how live and real time this is. We're getting it here. We're almost there. We're almost there. There we go. I think I can see that now. Yeah, I can see that now. So notice on the, I just want to bring this to your attention. We have multiple sections we have to go through here, right? Sorry, that's the lab section. Let me go back up. There we go. So here's the lecture exam, the lecture tentative lecture schedule. So I already talked about this before, but let's just mention it again. We have a lot of stuff to cover, so this lecture schedule is tentative, right? Because I might have to push it some of the lectures to the next day, or we might get done with something fast, right? But what I really want you to take note of is the days of exams, right? We have an exam on June 4th, which is this Friday. We have an exam on June 11th, which is this Friday. We have an exam on June 18th, which is this Friday. And we have an exam on June 25th, which is this Friday. Sorry, I keep on saying this Friday, but it's the Friday of that week. And you might be asking yourself why there's so many exams. Well, let me just tell you that if I only had one exam or two exams, there would be too much information covered on one exam, and it would be very difficult to study for. So this is the best way to do it. So just make sure that you remember that we have those exams. And if you guys take a look down here at the very bottom, Thursday is the last day. Thursday, July 1st is the last day of our class. And that day will be the final exam, and it is cumulative. Okay? What that means then is that it's going to have the material from everything of that week, just like a lecture exam would, but it also has everything else from the very beginning of the semester. Again, that final exam is for 25% of your entire grade. Please take it, okay? Please take it. Okay, so I want to go ahead and go over to show you some stuff here. We'll talk about lab flow in the pre-lab lecture video. So I'm not going to talk about that here, but what I do want to show you is Wiley Plus. So on well, actually, let me go back to Blackboard real quick. So in Blackboard, one of the menu options we have over here is important handouts right there. When you click on important handouts, you have the lab flow enrollment instructions, which you have to do to participate in lab and get a grade for the lab, because the lab is also worth 75% of your grade. But then you also have the Wiley Plus enrollment instructions, right? And they'll show up here. You can see then that in the Wiley Plus enrollment, you have these steps. The first step is to go to wileyplus.com/go/login, and then just follow those directions. Once you log into Wiley Plus, you will see something that looks like this. Right there, like this. I'm teaching multiple classes, so I have multiple sections here, but yours is going to be the one that's only available to you because you use the access code to access it, right? And when you go to it, I'll switch over to student view here so you can see things the way you would see it, right? We're not going to do much with Wiley Plus other than this. When you click on Wiley Plus or Wiley Course Resources, it will take you to this page here, right? Where it has course resources, okay? And the thing I want you to see about this is that, for example, when you go to the first chapter, the review of general chemistry, and click on that, the window there, right? You can see that there are a whole bunch of different things here to help you, resources here to help you learn, or help supplement your learning in organic chemistry. For example, learning about induction and polar covalent bonds, right? You can click on that there, and it's a video and teaches you how to do certain things, right? There is sound, but I have sound turned off right now on my presentation computer. So you can see here someone's teaching you how. It's actually David Klein. He's the author of the textbook. So feel very privileged and very fortunate that he's the one that's actually teaching you this stuff in this video. But this stuff will help a lot, and as we go through the lectures, I'll tell you about which ones to look at in the Wiley Plus. That being said, I think we can go ahead and get started with the lecture. This is actually lab flow right here, and we'll talk more about lab flow in the pre-lab lecture, which will be a separate video. Okay. So let's minimize that, and we'll start the lecture now. Right there, I think. There we go. So, again, Organic Chemistry 1. We are CHEM 2423, section 20005, and this is the first lecture, and my name is Dr. Fong No, and let's go on and get started. Let me make sure I have my marking material, my pen working here. And I think we'll go with red today. Oh, red's already chosen. The color of the dark side, right? Anyway, next then. So, I already said this before, but let's ask the question, what exactly is organic chemistry? Well, organic chemistry is the study of carbon-containing molecules, right? And their reactions with other molecules, right? Well, how do molecules actually, react with things? Well, for one thing, there's this thing called collision theory, where molecules just collide with each other, and then they start mixing, and then they react, right? And that collision itself will break bonds or make bonds, right? And when that happens, you have a reaction that occurs, where you're decomposing a molecule or you're forming a new molecule, right? The important thing to remember is that in organic chemistry, we focus mostly on the electrons, right? Electrons are very important in organic chemistry. And you can see it by this little example here. We have here a hydroxide, right? A base. And we have a methyl iodide right here, right? And one of the things that you learn how to do in Organic Chemistry 1 is learn how to push electrons, where you show the flow of electrons from one molecule or atom to another, right? And that's the entire basis of organic chemistry, learning how to do those electron pushing exercises so that you can predict reactions, right? So generally electrons are negative, right? And so electrons like to go towards things that are positive, also known as electron sinks, right? You already learned back in general chemistry, I hope, that oxygen right here is super electronegative, right? We'll talk more about that in a second, but it's super electronegative, right? So it's got a lot of electrons right there, okay? And then this carbon right here, right? It's actually sharing electrons with all these other atoms here, the hydrogen, the 3 hydrogens, and the iodine. So it's actually more positive. Just stick with me here. It's a little bit more positive, right, than the electron density of the oxygen. So those electrons flow from the oxygen to the carbon, right? To the carbon. Okay. So when you're looking at a double-sided arrow, that means 2 electrons, right? 2 electrons go from the oxygen of this hydroxide, and it attacks the electron sink or the partially positive carbon, right? Well, when it does that, the problem is that, if you remember from Gen Chem, carbon can only have 4 bonds. Its valence electrons is only 4, right? So it's got to lose 1 bond somewhere. Well, what bond does it lose? Well, remember iodine is also super electronegative too, right? So it will gladly take back its electron that it was sharing with carbon, right? So that carbon can form 4 bonds now, right? To give you this methyl group with hydroxide on it, right? And an anion of iodine, or also known as iodide, right? Also known as iodide. So literally what you've done here is you made methanol, right? Because it's a methyl group, yeah, with a OH, right? Methanol. Well, much more familiar. It was just Memorial Day, so we're much more familiar with ethanol, right? Which is this thing, right? 2 carbons and an OH. But here we have methanol. You can't drink methanol. That's bad for you. That will kill you. We'll talk about that later. But anyway, so your products then end up being a methanol and an iodide ion, right? And if you remember from Gen Chem, just in this reaction alone, we have maintained the certain conservation of mass and charge that is important, right? Because we have a neutral molecule here, a neutral molecule here. There's only one of each. We also have a negatively charged molecule there, or not molecule, but ion there. Now we have a different ion that's negatively charged. So we conserve all those things, right? You will see, for the vast majority of your career in organic chemistry, this kind of thing happening, where electrons are being used to predict the type of reactions that occur, right? So we focus on the electrons. I've spent way too much time on this first slide because we have a lot of slides to get through. So the rest of this is going to be pretty fast. So why is organic chemistry important, you might ask? Well, like I said before, organic compounds contain carbon atoms, right? And organic compounds just turned out to be like in most of the things that we deal with in life, right? Like plastics, drugs, food, clothes, right? And also your entire body is made of carbon. So that's why organic chemistry is important. So the structural theory of matter, right? Why are bonds so important? Well, you can't really like determine what a molecule is just by its formula. And the reason why is because if you had a formula of a molecule and you had another formula of a molecule and they looked exactly the same, you would think that they were the same molecule, right? But it turns out that two molecular formulas could be two different molecules because they're connected, the atoms are connected in a different way. And so what that's called is called a constitutional isomer, right? So, and we have an example of a constitutional isomer here. We have dimethyl ether here, right? It's got 2 carbons, right? Let's write out its formula. 1 oxygen, right? And 6 hydrogens. Over here we have ethanol. Oh, I was just talking about ethanol. Again, we have 2 carbons, 6 hydrogens, oops, 6 hydrogens, and 1 oxygen, right? I'll tell you right now that you do not want to drink dimethyl ether, right? But you can drink ethanol, right? That's actually drinking alcohol, okay? So these two have the same molecular formula, but one is very bad for you to drink, right? But the other, because it will kill you, and the other one is like in beer, right? And whiskey and in rum. Okay, so let's talk about some common bonds, right, that form with carbon. Nitrogen, oxygen, and hydrogen, it forms bonds with carbon readily, as well as the halides, which are also known as the halogens, right? Fluorine, chlorine, bromine, and iodine. And as I said before, carbon is tetravalent, right? It can form 4 bonds, okay? It has 4 valent electrons, right? And you can see that from the periodic table, okay? We move on to nitrogen. Generally, it can form 3 bonds, so it's trivalent. Generally, oxygen can form 2 bonds, so it's divalent. But sometimes you might see like a O- with a single bond. But generally, when it's uncharged, it's got 2 bonds. And then we have the monovalents, right? The things that can only form 1 bond, which are the hydrogens, right? And then the thing that you need to really remember here is the X's. What does that mean? X is always a halide, right? A fluorine, chlorine, bromine, or an iodine, okay? They can form 1 bond, which makes sense because they're at the end of the periodic table, right? With only 1 valent electron. Yes, that's right. I don't know why I stopped there. Anyway, let's keep going. Oh, yeah, that's why I stopped, because I was going to tell you. Now, if you want some practice with figuring out valences and drawing constitutional isomers and such, right? You can go to the Wiley Plus and look at Skill Builder 111. That's Chapter 1, Section 1, for drawing constitutional isomers, right? That says isomers right there where my head is, by the way. All right, let's keep on moving. So let's talk about covalent bonding then. You remember back from general chemistry, I hope, that there's the covalent bonding and then there's ionic bonding, right? And in ionic bonding, there's like a transfer of electrons between like between two, from an anion and a cation, right? Or a cation and an anion, generally a metal or a non-metal. There's a transfer of electrons, right? So it forms an ionic bond, and you form like an ionic compound. So an example of that would be like sodium chloride, right? Where sodium is Na plus, and chloride is Cl minus, and the two of them are much happier together if chlorine gives its extra electron because of the minus to chloride because it's plus, so it's missing an electron, right? The two are much happier together that way, right? Because then they fill their outer electron shell. Okay, so that's the ionic bonding. But you also remember then from general chemistry, there's covalent bonding, right? And we taught you in general chemistry very briefly what covalent bonding is, and what it is it's a sharing of electrons, right? Well, we're going to dive a little bit deeper into it now, okay? I already said this, oh my gosh. A covalent bond is a pair of electrons that are shared between two atoms, right? So the example that we have here is two hydrogen atoms, right? And they come together to make the hydrogen molecule, right? H2, right? Single bonded. And that would be a covalent bond, right? So how does this actually work out, right? Like in real life? Well, on this chart here, on the y-axis, well, let's start with the x-axis first. On the x-axis, right, we have the distance of two atoms, okay? Let's just say the two hydrogen atoms. But then, on the y-axis, we have the amount of energy. And you recall from general chemistry that most of the time, molecules, atoms, or anything in chemistry for that matter, wants to be at the lowest energy possible, right? It's the most stable, right? So when two atoms are far away, right, there's not much energy happening between them, right? So it's like zero energy, right? But then they can come a little bit closer to each other. And as they come closer to each other, the energy goes down, goes down, goes down, goes down. And why is that? Remember that a lot of atoms want to have a full electron shell, right? And this hydrogen atom only has one in its orbital, right? It should have two in that first s orbital. And this hydrogen atom only has one in its s orbital, right? Both of them want to have two in their orbital, their s orbitals, right? So that's what attracts them to each other in the first place, okay? And so as they get closer and closer to each other, and those electrons start filling in the missing hole, right, in their lives, right? The energy gets lower and lower and lower and lower and lower until it reaches a peak, valley, right? Where the energy between the two atoms are at its lowest, right? And when you reach that, you formed a hydrogen molecule, right? Or an H2 molecule. But the funny thing about that is that there's still electrons, right? And these can still repel each other, right? Not to say nothing of the fact that the center of the hydrogen is positively charged, right? Both of them. And those repel each other too. So the closer they get after they reach that valley, the energy starts going up. And up and up and up. Right? But the point is, if they get too close, as they get closer and closer to each other, they might repel each other away from each other, right? But the point is, though, two atoms form a molecule because they want to get to this valley of lowest energy right here, right? This valley of lowest energy, right? And you can see that this here is negative 36 kilojoules per mole, right? Which is pretty low energy, right? It wants to be that way. It wants to be that way. So, I already went through most of this in the last slide because I talked too much, right? But how do potential energy and stability relate? Well, I just said that. right? As they get closer and closer to each other, they can form that molecule of hydrogen gas, hydrogen molecule, right? And that bond forms because they're sharing electrons so that they can fill their outer shells, that little hole that they're missing in their outer shells, right? So attractive forces between positively charged nuclei and negatively charged electrons, right, keep the two atoms at an optimal length, right? The length that keeps them together as a hydrogen molecule, or in this case, hydrogen gas, right? Repulsive forces between two positively charged nuclei also keep them at a good distance. And then repulsive forces between negatively charged electrons also keep them at a good optimal difference, right? Okay? Good optimal distance or length, right? If they get too close to each other, though, there'll be repulsion and, kablooey. But nature does a pretty good job of keeping us at our most stable most of the time. Next. So, a quick review of general chemistry. Right? A quick review of general chemistry. Protons have a +1 charge, and neutrons have a neutral charge, right? And they reside in the nucleus. Electrons have a -1 charge. They reside in the orbitals outside the nucleus. The valence electrons are the electrons that are in the outermost shell, right? They also tell you how many bonds an atom can form. And so if you look at carbon as the example, which electrons are the valence electrons in carbon? Which electrons are the valence electrons, right? Well, those are those four that are on the outer orbital, right, that make carbon a tetravalent atom, right? This is important because valence electrons, like I keep on saying, are what involves bonding, right? Or bonding involves valence electrons. There we go. I said that backwards. So, wow. I alluded to this before already, but let's talk about valence electrons, okay? Counting them. You can always calculate the number of valence electrons by analyzing the electron configuration. Or, for group A elements only, you can just look at the group number, right, on the periodic table. Okay? Group number on the periodic table. So, notice here, carbon has 4 valence electrons because it's in group A, or group A molecules, right? Group A atoms, okay? You don't have to worry about, the group B elements because the group B elements are here, the transition metals. Things like iron and cobalt and nickel and things like that. That's very complicated. We'll talk about that later in life, okay? Then here, nitrogen has 5 valence electrons, right? But 3 of them are lone, and that's why it's trivalent. Oxygen has 6 valence electrons, right? 2 of them are lone, right? So that's why it's divalent. And then the halides, or the halogens, right? They have 7 valence electrons. 1 of them is lone, right? And so that's why it's monovalent. And so, for practice, you can go over to Wiley Plus, Skill Builder 1.2, to draw, practice drawing Lewis structures. Okay, Lewis structures. Okay. So, let's just do a quick review of how to do the Lewis structures, right? First thing you do is you draw the individual atom using dots to represent its valence electrons, okay? So then you put the atoms together so they pair electrons. So pairs of electrons to complete octets. Remember, they like to have 8, right? An octet is 8 in their outer shell. So we can look at it here and see nitrogen, right? Remember, it was in group 5. How many valence electrons does it have? 1, 2, 3, 4, 5, right? And notice 3 of them are lone. Or lone. I apologize. I'm confusing you because in the last slide I said they're lone. generally always in organic chemistry, you refer to lone as lone pairs. What I meant to say was that there are three of them, right, that don't have full, that are not, there are three electrons that don't have, they're not paired. There we go. That's the way to say it. Right? There are three electrons that are not paired. So let's just go back here real quick so I can say that again. Carbon has four valence electrons, right? And all four of them that are valence, none of them are paired, right? And that's why it's a tetravalent. Okay. And then nitrogen has five valence electrons, right? One of them is a lone pair, right? That means it's a pair of electrons together. And then three of them are not paired at all, and that's why they have the ability of forming bonds, making them trivalent. And then oxygen is divalent because it has two lone pairs, right? From the it has six valence electrons, right? It has two lone pairs of electrons, but it also has two electrons that are not paired. And then the halides, or the halogens, they have seven valence electrons, right? Three of them are paired, one is not, right? Three sets are paired, one of them is not, that means there's only one bond, and making them monovalent, right? So taking that to this next step here, let me erase what I drew here, right? We're looking at nitrogen. And nitrogen, as you can see, does have that one single lone pair I was talking about. So what about the other electrons that are valence, right? Because it's supposed to have five. Well, the other three of the five are not paired. 1, 2, and 3. And that allows nitrogen to be a trivalent atom, forming three bonds. I apologize for confusing you earlier. I kept on saying they were alone. They are alone because there's only one electron there and they're not paired, but we don't refer to them that way. They're just unpaired electrons is how we refer to them. Lone pair, right, is exclusively used to identify these guys up here, okay? A pair of electrons that don't do any bonding, okay? Then you take a look at these hydrogen atoms, right? Hydrogen is also monovalent, right? And that means that then it has unpaired electron available that it can share with the three unpaired electrons of nitrogen, forming our friend here, NH3, or ammonia. And everybody's very familiar with ammonia, especially if you're like, if you have a fish tank. I have a saltwater fish tank at home. Thank God none of the animals died during the deep freeze we had in March. That was a rough time. But when you have a saltwater fish tank, I've never had an actual freshwater fish tank, so I don't know if it's in freshwater tanks. But in saltwater fish tanks, the very first byproduct of waste from any of our animals in saltwater fish tanks are ammonia. So, yes, ammonia and ammonium. And ammonium is just an H4 plus, if you recall, right? NH4 plus. That's the ammonium ion, right? Which is very related to ammonia. How? Because the ammonium ion just looks like this. It has hydrogens on all four sides, right? Instead of having just three hydrogens, which is a problem, right? Because ammonia is already neutral, right, with all of its electrons in 8 form, right? So what happens then is that this extra hydrogen up here has to borrow an electron, right? That's one of the lone pairs. And when it does that, it turns nitrogen to a positive, right? Because it literally took one of nitrogen's electrons. So now instead of it being neutral, it's positive when it becomes an ammonia, right? Ammonium ion. Let's keep on trucking. So this is just instructions again on how to do the Lewis structures. They're super easy. You should already know how to do them from general chemistry. Draw the individual atoms first using dots that represent the valence electrons. Put the atoms together so that they share electrons and make complete octets. And again, practice with with Skill Builder 1.2. And I already said this before. Again, I just keep on skipping ahead and I apologize for it. Right? We have formal charges, right, for our ions, and an ion is a negatively charged atom, right? So that's something like Cl minus. And a cation is a positively charged atom, like an Na plus. Opposites attract, because this nitrogen will happily take this extra electron, right, from chlorine to make sodium chloride, table salt, right, so that they both can have full octets. Okay? Full octets. Atoms in molecules sharing electrons are typically neutral, but they can also be ionic or cationic. You'll see that later on. And then to determine the formal charge of an atom in a given molecule, compare the number of valence electrons that it owns based on the bonding pattern to the number of valence electrons that are that the atom needs to become neutral. Right? This is all review. You should know this already. So, let's talk about the formal charge distribution then of methanol. Okay, of methanol. Well, I apologize. That's not even methanol because there's not a hydrogen there, but it looks a lot like methanol. So the point of this is that we know that the carbon here is tetravalent, which means it has 4 electrons, right, that are capable of bonding. Okay, so it's bonded on 3 sides with hydrogens that are neutral, right? But when you look at this oxygen right here, it's kind of weird, right? And this is why I made the mistake of calling it hydroxide, or not hydroxide. I had made the mistake of calling it methanol, right? Because generally you see a neutral compound of methanol, and it looks like this. It looks like that, correct? Right? That's what methanol looks like. But here, we're missing the hydrogen, right? We're missing the hydrogen. So the problem here then, right, is that oxygen has its full octet up there, but in doing so, having its full octet, but not sharing its electron with something like a hydrogen right there, right, makes it so that this oxygen is now negatively charged. Then I actually drew that for you earlier, remember? I showed you an oxygen that was an O minus. Well, what is an O minus? Literally an oxygen atom with an extra electron. That's an O minus. Because over here in methanol, that oxygen looks like this. With 2 lone pairs, right? With 2 lone pairs. But then it became by itself, and it literally took this bond here from hydrogen, giving it an extra. It took that extra electron, or it took that electron from hydrogen, right? And now it has an extra electron. It's no longer neutral. It's got a negative charge now. Okay? So the formal charge of this oxygen here is minus. And you'll see that a lot, actually. You'll see that a lot. And you'll see hydrogen go pop off, right, by itself with that missing electron often too. And why is that? Because when it pops off, leaving behind the electron with oxygen, since it lost an electron, it actually becomes plus charged. So it's a hydrogen plus. And that should look very familiar to you because that's an acid, right? H plus ions, what are those? They're acids. Okay? Does that make sense? Right? It can join up with a water, right? And become an H3O plus, which is also an acid, based on the Bronsted-Lowry acid-base theory, right? This one right here, H plus, is just the Arrhenius acid-base theory, where we have H plus ions being added to solution in an acid in acidic conditions. But in Bronsted-Lowry, it's an H3O minus. I'm sorry, H3O plus, right? That is representative of an acid in Bronsted-Lowry. Okay? There's also Lewis acid-base theory, but we'll talk about that later. Let me make sure I didn't forget anything here. Carbon needs 4 valence electrons to be neutral. We knew that already. Carbon is surrounded by 8 electron pairs, but it only owns 4 of them, 1 from each of the bonds. Since carbon owns 4 electrons and needs 4 electrons to be neutral, it does not have a formal charge. Right? It is neutral. But oxygen, on the other hand, right? It needs 2 bonds and 2 lone pairs. But it doesn't have that. It's got 1 bond and 3 lone pairs, which means it's got a formal charge of what? Minus. And I bet you anything that the next slide is going to say that same thing, so we can skip it. Oh, there it is. See, now it's telling you to look at the oxygen right there. Right? What is the formal charge of the oxygen? Right? What is the formal charge of the oxygen? And I'm just going to minimize this for my head real quick so you can see that it is -1 charge, just like I was saying. Right? So this should be a -1. Because it's got 3 lone pairs and a bond. Okay? So for some practice with calculating formal charge, check out Skill Builder 1.3, and we will go for it. Let me come back. So, I'm getting parched. Let me take a drink here. My girlfriend was really nice to me, and for Christmas she got me this really cool tumbler, and it's like a resistance tumbler, you know, from like Star Wars, except it has Captain Rex's helmet in there, which is really cool. So it's like a Star Wars Rebels kind of thing. And she knows I really like, you know, the Clone Wars and all that stuff. And what's even really cooler is that on the back, you know, a very interesting quote from Captain Rex from the Clone Wars. In my book, experience outranks everything, right? That's interesting, right? For you Clone Wars and Star Wars fans out there who's watching me lecture today. All right, let's keep on trucking. We have a lot of stuff to get through. Holy mother, we're only on slide 15. I forget how many slides I have here. Who cares? Let's just keep going. So let's talk about electronegativity then. We already spoke briefly about electronegativity a second ago, right? As you go towards the right of the periodic table and up the periodic table, things get more and more electronegative. So fluorine here is actually the most electronegative on the periodic table. Okay. You also know that oxygen is super electronegative too, right? Things like that. If you remember that fluorine is the most electronegative atom, then you can always remember that the relative electronegativity of the atoms in the same column or the same row of the PTE. I don't know what that means. What does PTE mean? Forget about that. Anyway, electronegativity. How strong? So, what is electronegativity? It's how strong an atom attracts shared electrons, and in this case, you know, in all cases, to the right and up is the highest electronegativity, and we already knew that fluorine and oxygen are super electronegative. Right? Next. So there are three types of bonds, right, that we need to go over. We already talked about the covalent bond. In a covalent bond, electrons are shared between 2 atoms, right, where the electronegativity difference between the 2 of them is less than 0.1, and that's a covalent bond. We have a polar covalent bond then, at an electronegativity difference between the 2 atoms of 0.5 and 1.7. And then for ionic bonds, the electrons aren't really shared, right? But also, you know, because we like to have numbers here to show objectivity, right? The electronegativity is actually more than 1.7, right? And then you can be assured that it is a ionic bond. And my head's blocking it again. All this is an OH minus, right? 3 lone pairs on the oxygen, right? And remember, when you have 3 lone pairs on an oxygen, what do you get? It's got 1 extra electron than it needs because it's not sharing it with something. It's a negative charge, right? Put the opposites attract together, and what do you get? NaOH, sodium hydroxide, right? My friend and yours. Oh, also, before we get too far, you know, this is clearly a covalent bond, a carbon between a carbon between and a hydrogen, also a covalent bond, right? But the interesting thing to notice here is that in a polar covalent bond, we have a carbon and an oxygen here, and we know that carbon is less electronegative, a lot less like electronegative than oxygen is, and oxygen is more electronegative. So we use these little symbols here to denote partial charges, right? Partial charges. So this is partially negative and partially positive. Makes sense. Oh, I'm sorry. I keep on getting ahead of myself. So let's take a look at the carbon-carbon, right? It's just a covalent bond. These have the same electronegativity, right? Carbon and carbon. But then you have a carbon-oxygen bond here. And electrons tend to shift away from the lower electronegativity atoms to the higher electronegativity atoms, right? So I said this before, where the electrons will go towards the oxygen, or the thing that's more electronegative, right? Giving you a partially positive carbon and a partially negative oxygen, right? And remember I was talking about before how you have a partially positive carbon, and it can be attacked by electrons, right? So that it can become another molecule, right, in a reaction. Electrons like to go to electron sinks, or positive carbon centers. Here we have the opposite going here, right? Lithium is actually less electronegative than carbon is, right? So if you draw it the same notation with this here, the electrons are flowing towards carbon, right? But really, though, this is kind of an ionic compound, right? Because lithium is a metal. It's got a positive charge, right? And carbon here has a negative charge. Here's a very very convenient little chart that we have here. Things that are just regular covalent, which is carbon and hydrogen, and then the polar covalents, and then also the ionics, right? With a very large electronegativity difference compared to the very small electronegativity difference with the covalents. So polar covalent bonds and the distinction from ionic bonds, right? We were just talking about this a second ago. This lithium methyl. I wonder what you call that. We'll just call it methyl lithium. Some bonds are acceptable to write as a covalent bond or ionic bond, as is in the following example. We have methyl lithium here. Just so you know, I may be a chemist, a PhD chemist, but I do not know the name of every single molecule in the world. I think this is methyl lithium, but we'll just keep on trucking with it, okay? So you can draw it like that, or you can draw it like it's an ionic compound, right? Where the carbon here has a -1 charge, right? Because it's got 3 bonds. It's supposed to have 4, and an extra electron, so it makes it a minus charge. And then you have the lithium, which is the cation, the metal cation, and which is sorry, lost my train of thought. The methyl is the anion here, and the metal, or the lithium, is the cation here, and they become an ionic compound. The electronegativity difference is 1.5, right? So it is actually on the cusp of being a polar covalent and ionic compound, right? If you look at salt, though, there's a really big difference, right, between sodium and chloride, right? So that's definitely an ionic compound. For practice with this, check out Skill Builder 1.4, Locating Partial Charges. All right, so now that we've got a lot of that like basic general chemistry stuff cleared up, and I don't know if it's cleared up or not, but at least we went through it, as a review. We can talk about drawing structures, right? Bond line structures. Some people call them line angle structures. I think I've always taught and learned it as line angle structures, but what they basically are is that if you were to draw a molecule like amoxicillin here, which is an antibiotic, out, it'd be super confusing, right? Because there's so many H's here, right? Look at all these H's. It just looks very confusing. There's a crap ton of H's, hydrogens, right? Well, in a line angle drawing or a bond line drawing, right, the H's, the hydrogens, are just assumed, right? They're implied. And what that means then is that if you see a carbon, for example, this one right here, it's got 3 bonds to it. This bond right here, this bond right here, and this bond right here. Excuse me, this bond right there, right? 1 double bond and a single bond. And absent any other charges or notation at that carbon, we know that there's a hydrogen right there, right? We know that there's a hydrogen right there. Same thing over here. We know that there's a hydrogen over here, right? It's implied. Because absent any other charges or any other notation, right, that carbon is a normally tetravalent carbon, which means it can form four bonds, right? And since it's absent any other charges, and it's got 3 bonds already connected to it, then we can assume then that there's a hydrogen connected to it. And what that does for us is that we can draw out amoxicillin here without having to draw out all these hydrogens, right? Like, for example, here, there would be 3 hydrogens drawn out, right? Because we assume that there are 3 hydrogens there because there's only 1 bond to that carbon right there. So, at every single, like, point here, there's a carbon. Those are all carbons, right? And we can leave out the carbons, too, the C's, too, because, it's organic chemistry. It wouldn't be organic chemistry unless there were carbons there most of the time, right? So here is a carbon, right? We call it a carbonyl carbon. Carbonyls are double bonded oxygens to carbons. And there's 4 bonds here. There's one right there, and one right there, right? The double bond. And then there's 2 single bonds. So there's no hydrogens attached to that, right? Because all the bonds are occupied by other bonds. So you don't have to do that. The other thing that we can lose too in a line angle drawing or bond line structure, right, instead of having to draw it out like this, which is not incorrect, but it just takes a lot longer, is that we can lose the lone pairs, right? We already know, for example, that when oxygen is neutral in a molecule, right, it has 2 lone pairs of electrons, okay? So we can then assume that these lone pairs are there, just like that, without having to draw them, because absent any charge or any other notation, those lone pairs are implied to be there, and so we don't have to draw those out either, right? In this normally very Lewis structure, right? This Lewis structure of amoxicillin. Also, we have nitrogens right there too. We know that nitrogen has a lone pair, right? 1 lone pair. The other 3 are occupied by bonds. We don't have to draw those either, but we know those are there as well. All right, we know those are there. Those are there as well. Talking a lot. Let me take a breath. And then also another thing here that's interesting is sulfur. Sulfur is in the same group as oxygen, right? So it's got the same electron configuration in the valence shell. So it's also got 2 lone pairs that we don't have to draw because we're doing line angle drawing, right? So amoxicillin is actually very interesting. It's an antibiotic, and I just wanted to erase what I just drew here, but you'll see it in the video. You can always rewind. It has this cool little thing here, right? And that's called a beta-lactam. And that beta-lactam is the quintessential structure of all penicillin-based like antibiotics, right? And the reason why is because that beta-lactam there is instrumental in its activity as an antibiotic, right? It inhibits the cell wall production in bacteria, and the reason why it can do that is because this carbonyl carbon right there, that's in that little square, right? You remember from a Gen Chem, right, that when you have a carbon, its most when you have a four bonded carbon, its most stable structure has a bond angle of 180 degrees. Oh, sorry, not 180. Sorry, 109 degrees. Right? That's its most stable. Okay. Well, it turns out that when you have a carbonyl, which is a carbon connected to a double bonded oxygen, right? Like that. This bond is actually 120 degrees. Okay? But this is a square. To say nothing of the fact of the strain, the bond strain on the nitrogen, right? Because it's like trigonopyramidal, right? So that's got to be more than 100 degrees. So having these things in the strain bond formation right here makes it very active. And when it's very active, and we'll go through this in painful detail later on when we talk about like biochemistry, which is my specialty, and antibiotics and bacteria and all that mess, right? It makes it so that this bond right here can break real easily. And when it breaks real easily, it can actually attach to an enzyme that bacteria use. I believe it's called peptidoglycanase. I could be wrong, but I think that's what it's called. And it keeps it from being able to build its cell wall. And when a bacteria can't make bacterium, I guess, can't make its cell wall, it dies. And that's the basis of a beta-lactam antibiotic because of that structure right there. It's so interesting, isn't it? It's super interesting. Again, I'm spending too much time on this one little thing, but I want to point out interesting things to you. Let's keep on going. So more line angle drawings, right? I don't really have to go over this. I've already said this before. These are all, wherever you have a little angle there, right? That's the carbon, and absent any other charges or notations, the rest of it to fill up a tetravalent carbon is hydrogens, right? And then the other thing to remember here, though, is like, this is a triple bonded, carbon right here. So the only extra hydrogens will be over here, right? Because this alkyne, which you'll learn more about alkynes later, triple bonded carbon molecules, right? This carbon here and this carbon here already has 4 bonds, so you don't need to have any hydrogens on there, right? Zigzag. See, I don't know why they don't just call it the line angle thing here. If they're going to call it zigzag format, whatever. Next. Oh, we're really going to do this. We're really going to go through this ad nauseum here. Just again, I'd already told you about that, right? Where absent any charges or any other notation, right? If you don't see a hydrogen there and the carbons are not fully bonded with all 4 bonds, then you assume that it's a hydrogen that's attached to it in the line angle drawing. And you can practice this with the Skill Builder 1.5. Ooh. Let's keep on going here. So we're not going to jump too deep into this because you'll do this a lot in PChem, in physical chemistry, okay? But in the 1920s, quantum mechanics, right, actually was established, and it explained the wave properties of electrons, right? And the solution to the wave equation are wave functions, and these wave functions, the 3D plot of these wave functions, right, gives you an image of an atomic orbital, right? And an orbital, like we were just discussing before, is where electrons reside, okay? Or it's where we think they reside, where we think 99% sure that's where electrons are, right? And again, this is a lot of math that you don't need to know for this semester. The wave function and the wave equation, a lot of math that you don't need to know for this equation. But just know that those mathematics determine a 3D plot in which, you have a probable location, right, where an electron resides. Okay, and you'll learn a lot more about that in PChem That is beyond the scope of this class. So, atomic orbitals equal electron density. Okay. And I think I said this a little bit before, but the atomic orbitals are either s orbitals or p orbitals. And remember, I was talking about before how the p orbitals come together and make a single bond, right? Well, the electron density then is a term that is used to refer to the probability of finding an electron, and the orbital shape is about 90 to 95% of the space where the electron could probably exist. My bad. I said 99%, but it's 95%. Okay, 95%. So we think of an atomic orbital as a cloud of electron density. Okay, so here's an s orbital right here. It's literally a shell. It looks like a shell that's around the atom. Okay, that's an s orbital. And then these are p orbitals, right? And they are aligned with the axes, right? Axes, whatever. The axes, right? That originates with the atom at its origin. That was redundant. Originates at the atom, whatever. You got me. So this p orbital here is actually the py orbital, because this p orbital is on the y-axis. This is the px orbital on the x-axis, right? And this is the pz orbital. This particularly confused me before in life when I was learning it too, because it looks like pz right here is in the plane, like flat. And when I was, I used to do a lot of 3D printing. Well, I still do a lot of 3D printing, and the z-axis has always been like the up and down axis on the 3D printer, so it gets confusing a little. But just remember to look at these things. These drawings, and they'll always tell you which axis is which, right? So electrons behave as both particles and waves, okay? But you ask yourself, how can they be both? Maybe the theory is not yet complete. We don't know yet. The theory does match with experimental data, and it has predictive capability. Again, this is beyond the scope of the class, right? What the theory, all that stuff could be, right? But the point is this: like a wave on a lake, an electron's wave function can be positive, negative, or zero, right? And when it's a zero, it's a node. Okay, so here's your node, and here's its positive, and here's the negative. Okay, here's a positive, here a negative. Okay, we take that to the next slide. And then we can see then that here's the positive, here's the negative, and the node of a p orbital. Okay, of a p orbital. Let me make sure there's nothing in here I need to tell you. Yeah, okay. The sign of the wave function will be important when we look at orbital overlapping in bonds, right? That's important to know, because we'll see that in a second. So, I already told you guys this, but we'll go over it again because there's a slide for it now. Electrons are most stable in the lowest energy if they're in the 1s orbital, right? Which is this guy right here, the 1s orbital, right? So when we were talking about the hydrogen gas earlier, H2 gas, right, or the molecule, right? It only has 2 electrons, and those 2 electrons form a single bond, right, in the 1s orbital. So it's a very stable molecule. It's in the 1s orbital. But sadly, other molecules and other atoms have more than just 2, and they have to expand to the other orbitals, right? And so the 1s orbital, like every atomic orbital, can have up to 2 electrons in it. If there are more electrons in the atom, they fill up the 2s orbitals, which is this one. The 2s orbital also is just a sphere around the center atom. And then the 2 p orbitals, right? Which I alluded to before. I told you they were the py, px, pz, but they are really the 2 p orbitals when you're talking about like electron configuration and stuff, right? These 3 p orbitals, these 2 p orbitals, right? They're all degenerate orbitals, which means they all have the same energy. So let's take a look at some examples of some common elements in their electron configurations, right? Like I was saying before, we have hydrogen here, and it's only got a single electron, and it's 1s. When you bring two hydrogen atoms together, those two electrons reside in the single bond that's formed when the two 1s orbitals overlap, right? And it's a very happy atom, or molecule. Helium has two in the 1s, so it's got a full valence shell, right? Which is why it's a noble gas, right? It's quite happy on its own. We've got lithium here with two electrons in the 1s and then one electron in the 2s orbital, right? So remember, these s orbitals only hold two electrons, right? So here, lithium then is what? It's missing one electron, okay? And since it's missing one electron, really, it's like a plus, right? And that's why it's a cation, and that's why I'd rather just have an anion transfer its extra electron to itself, to lithium, right? So like lithium chloride, okay? Because chloride has an extra electron. Beryllium, it's got two full shells right there, right? Two in the 1s, two in the 1s, two in the 2s, right? Boron, right? It is oh yeah, here we go. It's got a single unpaired up there in the 2p orbitals. Carbon has a 2 unpaired there. Boy, that's weird. How does carbon have 2 unpaired electrons, but it's tetravalent? I thought it would have 4 unpaired electrons. We'll get back to that. Just put a pin in that. Put a pin in that. You got nitrogen. 3 unpaired electrons right there. This is why. This is what? That's why it's got 3 bonds. That's why it's trivalent, right? Oxygen. 2 unpaired right there in the 2p. Divalent, right? Fluorine. 1 unpaired there. Monovalent, right? And neon, just like helium, okay? Full in all the shells, so it's a noble gas. But we got to go back to carbon here, right? What's going on with carbon? I thought I said it was tetravalent. It's only got 2 unpaired. How is it possible? I don't know. No, I do know, actually. Let's take a closer look at carbon. I think that's the next slide. Oh, no, it's not. We'll just put a pin in that. We'll get back to that. So there's a couple different theories when it comes to bonding, and one of them is valence bond theory. And in valence bond theory, what it says is that an electron is like a wave, right? And when you bring these waves closer to each other, and they're the same charge, right? The same sign, like positive, they can reinforce each other and become constructive interference, forming a bond, right? But when you bring two waves together that are opposite sign, well, these waves cancel each other. And when they cancel each other, it's destructive interference, right? It's destructive interference. So it turns out that in valence bond theory, right, only constructive interference can result in a bond, right? And, you know, valence bond theory takes a much more simplistic approach to how bonds form. We'll dive deep into molecular orbitals in a second. But let's use hydrogen gas again as an example right here, right? I got my hydrogen gas right here, and it's got this one little electron just floating around, flying around inside that little 1s orbital. I have another hydrogen atom there with its electron flying around inside somewhere in that 1s orbital. And when they come close to each other, there's a direct overlap, right? And it forms a bond. And before I was calling it the single bond. It is a single bond, right? But you should know, though, that when two s orbitals come together to make a bond, it forms a sigma bond, right? It forms a sigma bond. And that's what it says right here. Sigma bond. Even though my face is covering it. There we go. Sigma bond. Right? That's the sign for sigma. Or is it like this? There it is. That's sigma. Okay. I've never been good at drawing, Greek letters. Next. Oops, that's previous. Next. next. Here we go. So let's talk about molecular orbital theory now, right? Atomic orbital wave functions, right, overlap to form molecular orbitals that extend over the entire molecule, right? So it turns out that in the molecular orbital theory, these electrons can be anywhere in these orbitals around the entire molecule. Molecular orbitals are a more complete analysis of bonds because they include both constructive and destructive interference, right? And the biggest thing to remember here is that the number of molecular orbitals that are created must equal the number of atomic orbitals that were used, right? So let's use hydrogen again as a hydrogen gas again as the example. This is H2 right here. My head is blocking it, but it says molecular orbitals for H2. And remember what I said before. Hydrogen has one s orbital, one electron in its s orbital, right? One electron in its 1s orbital, the atom. And the other hydrogen atom has 1s orbital, has one electron in its 1s orbital, right? And as it comes closer to each other, it's much happier, right, when it's sharing those electrons, so it can have a full shell, right? And it forms a bonding molecular orbital right here, right? That's much lower energy. Notice this is energy here. That's much lower energy. But whenever you have a bonding molecular orbital, you also have an anti-bonding molecular orbital, right? And it's got a node in it right there where there's no electron density at all, right? But the important thing to remember here is that you started with 2 atomic orbitals, those 1s orbitals, right? One from each atom. And you end up with 2 molecular orbitals. Remember that. Remember that. That's important to remember. The anti-bonding orbital, molecular orbital, is higher energy because it has a node in it. And it kind of makes sense, right? Because think about it. Down here, when the electrons are sharing inside the bonding molecular orbital, it's got the entire space, right, of that molecular orbital to bounce around, be wherever it wants to be. That quantum mechanics says it can be at, right? But when you look at the anti-bonding orbital, this node here makes it so that there's no electron density there at all. To say nothing of the fact that the 2 signs here are different. So there's like more than half of the space missing for these electrons to go in. And if you can find an electron to a small space, it's going to be bouncing around like it's got tons of energy in it, right? So I'd much rather be in a bonding molecular orbital, right? Which is much lower energy. So just to conclude that little statement, that thought, when an atomic orbital overlap, the electron goes into the bonding molecular orbital rather than the antibonding in order to achieve, that says achieve, a lower energy state. So, I was saying before too that molecular orbitals actually expand over the entirety of a molecule, right? There are more than 2 molecular orbitals that exist for methyl bromide, right? Oh, that's what that was before. I kept on calling it methyl iodine, but I think it's methyl iodide. Yeah. So methyl bromide, but let's focus on only 2 of them here, right? You can see where many of the atomic orbitals overlap, and there are nodes as well, right? But notice the important part here is how the molecular orbitals extend over the entire molecule. So you see here, there's a node right there, right? There's nodes there. You know, wherever there's not any electron density, there's a node. Okay. Take a closer look at this. Each molecular orbital can hold 2 electrons, which we knew that already, right? It's just like atomic orbitals. But in the ground state, electrons occupy a lower energy molecular orbital, while in the higher ones remain unoccupied, right? So there are 2 phrases that we must learn here today. The first one is known as the highest occupied molecular orbital, also known as the HOMO, which is when you look at a molecular orbital diagram, which you just saw a second ago of hydrogen, what was the highest molecular orbital that was occupied? And that was actually that one at the very bottom, right? And then the next one that's important is called the LUMO, or the lowest unoccupied, right? The lowest unoccupied. molecular orbital. And these are important because they are what come into play when you're talking about chemical reactions. And I'll give you a quick example. When I did my research in my PhD school, I was studying bioluminescence, where electrons were getting promoted to these higher energy levels, and then when they through a chemical reaction, and when they relax, they would release light, right? Blue light with the molecule I was working with, luciferin, dinoflagellate luciferin, and we were trying to determine, it was going to a higher molecular orbital, right? And we weren't sure which molecular orbital it was, because at first we thought it was going to the LUMO, right? Because that was the one that was unoccupied, but it could have been going to the next one, right? So it gets really complicated. These electrons going back and forth when they're getting promoted and excited, right? They have a path that they follow in these molecular orbitals, and that dictates what kind of reaction it does. And let me just tell you that the light would be produced if it was going to the wrong molecular orbital, which, producing blue light in bioluminescence is kind of neato, right? Oh, finally, we're here at the... Let's talk about carbon. Remember carbon? We were like, what's going on here? Why does carbon have only 2 lone pairs, right? And I'm telling you that it's tetravalent. Am I not right? I'm a terrible professor. Oh my God, I have no idea what's going on here. No, I'm just kidding. There's actually a very good explanation for calling a carbon tetravalent, even though when you look at its electron configuration, right, it's only got 2 lone pairs, or I keep on saying that. Sorry, 2 unpaired electrons, right? So the first thing that we have to think about here is the fact that when you look at a carbon that has 4 bonds to it, those 4 bonds are equally distributed at 109 degrees all the way around that carbon atom, right? So the example of that would be like methane. So that's kind of weird, right? Because, we already know that we have 4 atoms here. Sorry, we have 4 valence electrons here, right? That need to be bonded, right? But some of these orbitals are different energies, right? And if they have different energies, there should be some kind of repulsion or attraction to make it not equally 109 degrees, right? So one of the very first things that people thought was that maybe there's some kind of excitation that occurred. And when that excitation occurred, right, one of the electrons from the 2s orbital went to the 2p orbital. And now you have your 4 unpaired valence electrons. But the problem with that is that the 2s orbital is lower energy than the 3 unpaired electrons in the 2p orbital, right? So, I mean, it would make sense then that it wouldn't be in methane, for example, a completely symmetrical molecule with its bonds all at 109 degrees, right? I mean, that's just weird. That's just weird, right? That's really weird. Oh, here it says, see, 4 equivalent bonds. How is it 4 equivalent bonds when you have a 2s right there, right? See, so the excitation explained why we can call a tetravalent even though it only has 2 unpaired electrons, right? When the excitation occurs, then one of the electrons from the 2s orbital goes to the 2p orbital, and now we have 4 unpaired, and now we can do 4 bondings, which means we are tetravalent now, right? But the problem, though, again, just so you remember, right, is that 2s right there, this 2s right here, is lower energy than the 2p's. So how is it possible then that we have equivalent bonds to make all the bonds of hydrogen around carbon and methane all 109 degrees, 109.5 degrees? That's weird. Well, our friend and yours figured this out. I believe it was Linus Pauling, maybe. Let me see here. I can't remember who it was. I think it was Linus Pauling. I may know my chemistry, but do I know my history? I don't know. I think you know what? If this was a YouTube video, you could comment below. But yes, comment below if this is a YouTube video, if you're watching this on YouTube. And tell me if I'm right. Is it Linus Pauling? I'm pretty sure it was Linus Pauling. So Pauling figured out then that maybe all of these orbitals, the 2s, right, and the 3 2p orbitals, undergo this thing called hybridization. And so when it does that, it forms 4 equal atomic orbitals with symmetrical geometry, right? Symmetrical geometry. So you hybridize the 2s and you hybridize it with the 2p, right? And now you have 4 atomic orbitals that are degenerate, which means what? The same energy, right? And now we can call all these orbitals the sp3 orbitals, right? So literally you're hybridizing these, okay? And in an sp3 orbital, one of them is an s orbital, and the other 3 are what? P orbitals, right? So that's why it's an sp3, right? It's an sp3 orbital, okay? And that forms our 4 equal energy symmetrical hydrogen bonds. Carbon-hydrogen bonds. So, and I already said this before, but we'll take it again, right? Since it is an sp3 orbital, one of them is s, the other 3 are p, which means then that this sp3 orbital has 25% s character and 75% p character, right? So this is what it looks like when you look at its wave function, right? It's a 3D representation, right? 75%, 25%. So we can then take a look at how we make methane, right? The 1s atomic orbitals from the 4 hydrogens, right, which are here, here, and here, and here, right? They actually overlap. Those 1s overlap with the sp3 hybridized atomic orbitals, which are here, 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 and here. And that's why you can form a methane that's all equal angled, all equal energy bonds, right? So that's an sp3 hybrid, or sorry, let me say that again. So that what that makes that is that, just remember that makes that carbon there sp3 hybridized, because there's more than just sp3 hybridization. We look at a molecule with a double bond, right? Like ethylene, right? Ethylene, or some people call it ethene, right? Ethene. It only needs 3 hybridized atomic orbitals because it's got a double bond, right? There are only 3 bonds that need to form to make ethane. The 2 from the hydrogen, right? And the double bond from the other carbon. So it doesn't need to have 4 orbitals like methane did. It only needs 3 hybridized orbitals, right? So the 1s, the 1 unpaired in the 2s orbital, right here, hybridizes with 2 of the 2 p's, right? And now we have sp2 orbitals, right? And they're all degenerate, right? And they can form bonds that are equal in energy, right? And in bond angle, right? The extra 2p there actually is not affected at all. And these 3 sp3 orbitals are lower energy than the 2p because it's an average of the energies between the s orbital and the p orbitals, right? It's an average, so it's less, okay? And notice, 3 orbitals, right? There's 1 s orbital and 2 p orbitals, right? Which is 3 orbitals. And then notice this. 1, 2, 3 sets of bonds, right? So if you go back to the previous one, in the sp3, right, you have the 1s orbital, 3 p orbitals, and you have how many bonds? 1, 2, 3, 4. So whenever a carbon has got 4 bonds to it, it's sp3 hybridized, okay? And then whenever a carbon has 3 bonds to it, what is it? It's sp2 hybridized. Okay? Come back to me if you need more help with that. Let's keep going. I'm on a roll. Oh, we've got to talk about bond character. So, if you've got sp2, that means you've got 1s and 2 p's, right? So, this is blocking it right here, but what it says right here is that you then have 33.3333, we'll just say 33% S character, right? Compared to the 67% P character of those bonds, right? And these sp3 orbitals right here, sorry, sp2 orbitals right here, are the ones that are gonna form bonds, overlap with another one of these carbons to form ethene or ethylene, right? And then the p2py orbitals, nothing's going on with them right now, right? Nothing's going on with them. So let's keep on taking a look here. So like I was saying before, in ethene, we have the two sigma, sorry, we have the two two sp2 hybridized orbitals, right? And they overlap, forming the single bond right here between the two carbons of ethene or ethylene, right? So the sp2 atomic orbitals overlap to form a sigma bond, right? But then previously I said that these p orbitals aren't really doing anything right now, right? But they aren't, not yet, okay? Because we're going to form that sigma bond first. And that sigma bond between the two sp2 orbitals gets formed. And then after that, when these orbitals overlap, the p orbitals, I believe they were the two py orbitals, right? We form a pi bond, right? We form a pi bond. And this is the double bond that we see in ethylene. What the heck is that? let me draw that again. Here we go. Double bond, right? And then H, right? There's ethylene. Okay. So one of these bonds here comes from the overlap of the sp2 orbitals to make a sigma bond, and the other bond comes from the overlap of the two py orbitals to make the other double bond. God, that's so amazing. Oh, and I already said this before, but here we go. We have our sigma bond right here, right? Which we already discussed. But then the two py orbitals, right, are overlapping up here, right? And though it looks like they're making two bonds, it's actually just a single bond, because remember, these are the same one, like same orbitals, right? So that overlap forms the bond, right? Because this is still, both of these are still the two py orbitals right here, right? Just different phase, and those together form the double bond. So this is still a double bond, even though it looks like a triple bond. Okay. Another thing to note: a pi bond is weaker than a sigma bond. Right? Pi bond is weaker than a sigma bond. We'll talk about that a little bit later. So, hybridized atomic orbitals in pi bonds, right? The pi bond is described in a similar way as according to molecular theory. Remember that red and blue regions are all a part of the same orbital, but the phases are opposite. I literally just said that. Just repeating myself. All right. So here we have our bonding molecular orbital right there for the pi bond, right? That's why I was talking about the two p's earlier, right? And then the pi anti-bonding right there is up here, and it has a node right down the center. So where would those electrons rather be? Down here, where they got a lot more room to breathe, right? And again, just to remind you, we have two atomic orbitals, and what do we have? Two molecular orbitals. Remember that. Oh, well, let's just talk about ethylene now. Wait, we just talked about ethylene. Let's talk about acetylene, right? Acetylene has a triple bond in it, okay? So how do we do a molecular orbital for a triple bond? Acetylene with a triple bond, right? Also known as an alkyne, triple bond. I forgot to say that before. Ethylene or ethene is called an alkene. That's the class or the group of molecules. And then acetylene is an alkyne, right? Anyway, so when you have a triple bond, right? We have a triple bond. you only have 2 electron domains, right? That single bond right there between the hydrogen and the carbon, and then the triple bond between the carbon and the carbon, okay? What that then means is that you only need to hybridize 2 orbitals, right? Right there. The other 2 orbitals from the 2p are not affected. So when you hybridize them, you get 2p orbitals. Sorry, you get 2 sp orbitals, and then you have the higher energy 2p orbitals that are unaffected, right? And remember, whenever you have your hybridized orbitals, it's an average of the p orbital and the s orbital, and that's why it's lower energy, right? And you have only 2 electrons in there, 2 lone pairs, right? 2 lone pairs in there. So the cool thing about that is, remember before when you had the sp3 orbital, hybridized orbital, that was an s and a 3 p's. You had a carbon that had 4 electron domains, or 4 bonds, right, on the methane. Then the next one, which was the ethylene, you had an sp2, that's 1 s orbital, 2 p orbitals, that's 3 in all, right? And what was that? That was a carbon with 3 electron domains, right? Or 3 bonds, right? On ethylene, it was a carbon with 2 H's off of it and double bonded to another carbon. So it only had 3 electron domains, or 3 bond domains, right? So now you look at ethylene, I keep on saying that, sorry, acetylene, right? And it only has 2 electron domains, or 2 bonding regions, right? And what do you have here? 2 atomic orbitals that have been hybridized, the s and the p, and that's it, right? So when you see something that has got only 2 bonding domains, it's an sp hybridized carbon, right? If you jump backwards a little bit, if it's got 3 bonding domains, it's sp2 hybridized because it's got 3 atomic orbitals. And if you jump back another one, it's an sp3 hybridized because it has 4 atomic orbitals for 4 bonding domains. Make sense? Right? I go over that with you a lot because there's going to be a lot of times when there's going to be like an exam question that's going to ask you, what hybridization is this carbon or this atom, right? So that's important, right? So let's keep on trucking along. How do these sp orbitals form their bonds? Well, let's take a closer look here, right? A closer look here at acetylene. Again, the sp hybridized orbital forms a sigma bond, right? The gray ones, right? Those are the hybridized ones. And then one of the p's right here, right, which its antibonding is on over here, the blue over here, right, forms a pi bond. And then the other p forms the second pi bond. And what do you have? It gives you a triple bond. I don't know why I wrote 3. I meant to say triple bond. Right? Pretty cool. Pretty cool. Yes, because these P's are overlapping. I just wanted to say that because it said that here, and I want to make sure that you knew that they were overlapping, right? Another plug, if you want to practice with identifying hybridization states, check out Skill Builder 1.7 in the Wiley Plus. So let's talk about the strengths and lengths of the pi bonds versus the sigma bonds, right? Which should be stronger, a pi bond or a sigma bond? Well, the sigma bond is considered to be stronger as it requires almost twice the energy, the bond energy of a pi bond to break, right? Which makes kind of sense, because a sigma bond is those hybridized orbitals with s and p's, right? And they have s character in them, and s character holds things together closer, right? So, which should be longer, an sp3 hybridized sigma hybridized overlap or an sp overlap? Well, the more S character in the orbitals, the shorter they will be. And I just said that, right? Because they hold things closer to each other. sp3 bond lengths are the longest, followed by the sp2s, followed by the sps, right? So the more S character there is in a bond, in a hybridized bond, right, or hybridized, excuse me, in a hybridized bond, then the stronger, excuse me, the shorter it is, right? And then also, sigma bonds that are using those sp orbitals, right, are stronger than pi bonds. Okay? Excuse me. Excuse me again, hold on. So this is just a table with actual numbers to demonstrate the last topic or the last statement. We have here ethane, right? It's got a single, excuse me, it's got a single bond right there, a single bond right there, right? And it's sp3 hybridized, right? It's sp3 hybridized. And its bond length is 1.54 angstroms, and its bond energy is 368 kilojoules per mole. We come here to the ethylene, or the ethene that we were just talking about, and it's got a double bond, right? So this guy is sp2 hybridized, right? This was sp3, right? There's more S character there, which means that the bond is shorter, right? And then also, it's got a higher bond energy required to break the bond, right? Which is 632 kilojoules per mole. And then we end then now with the triple bond, which is the sp hybridized carbon, right? It's got the shortest length at 1.2 angstroms and the strongest bond energy at 120 kilojoules per mole, right? Interesting stuff. Oh, well, let's talk about steric numbers now, right? So there's this thing called the valence shell electron pair repulsion theory. We talked about that before in general chemistry, not me and you, but surely you did with your previous professor in chemistry, right? And valence electrons, they're shared on lone pairs, they repel each other, right? And so when you say valence shell electron pair repulsion theory, right, that's talking about how much these electron pairs, excuse me, the bonds and the lone pairs repel each other. To determine a molecular geometry, start with the steric number, which gives you a quick prediction, right? So all these molecules here, we have methane here, we have ammonia there, and we have water here. 4 sigma bonds, 3 sigma bonds, 2 sigma bonds, 0 lone pairs, 1 lone pair, and 2 lone pairs. All that means then, when you add it up, is that the steric number is 4 for all 3 of those, right? What are the implications of that? Well, let's take a look at this then, right? If there's a steric number of 4, then it's a hybrid, it's an sp3 hybridized carbon, right? Which I already told you this before. If you have 4 electron domains, right, bonding or not, right, even with lone pairs, right, if you have 4 electron domains, then it's going to be an sp3 hybridized carbon, right? All these are sp3 hybridized, atom, sp3 hybridized atom, right? If the steric number is 3, then it is sp2, right? So we'll just use the carbonyl as an example again, right? You see the pair, right? There's electron domain there, there's an electron domain there, and then the double bond's electron domain, right? So that steric number is 3, and it's sp2. And then last but not least, 2 is, steric number 2 is an sp, right? Like the triple bond guy. I don't know what I draw there. Here we go. There we go. That's sp hybridized carbon. So, knowing the hybridization state of these molecular orbitals, right? These atomic orbitals, rather, to become molecular orbitals, right, can help you figure out the molecular geometry, right? And for sp3s, they are tetrahedral. And we talked about that before in methane, right? It is an equal energy, equal distance, equal angle, 109 degrees. 109.5 degrees um, angle for methane, or for methane. Yes, angles are equal. Okay. Ammonia though, ammonia is also sp3, right? The molecule is still tetrahedral, okay, but the angles are smaller. And why are they smaller? It's because it has one lone pair up there repelling. There we go, repelling the other electron domains down, right? So that's why those angles are smaller. And then water here, right, with its two lone pairs on oxygen, do even more repulsion, right? And so you can't see what it says here, but this right here says 105 degrees, right? So even smaller. 105 degrees. So it's even repulsing even further, right? So here's a quick little table, right? A quick little table to give you some common geometries, right? The geometry, molecular geometry described for only atoms bonded to the central atom. Electron group geometry includes lone pairs, okay? So the common molecular shapes that can be predicted with the Vesper theory are here, right? So we have methane here. Got 4 bonded pairs, no lone pairs, right? With a steric number of 4, and you have a tetrahedral. In both predicted arrangement of electron pairs and molecular geometry. Ammonia, though, only 3 lone pairs, only 3 bonding and 1 lone pair. You still have a steric number of 4. It's got the tetrahedral, like I was saying before, but its actual geometry is trigonal pyramidal. Water, 2 of each, right? Still has a steric number of 4. Also tetrahedral, right? But its geometry is actually bent. Boron trifluoride here, 3 bondings, 0 here, 0 non-bonding electron pairs, lone pairs. Steric number is 3. It's trigonoplanar, right? And then beryllium hydride, 2, 0, steric number of 2, and so it's bent, right? It's bent, sorry, it's linear for both. So the molecular geometry of sp3, importance of a lone pair, is what I already said before. These lone pairs actually do a lot of repulsion, right? Making it so that the bond angles are smaller, right? Making it so the bond angles are smaller. So let's talk about boron trifluoride, right? Remember that when you have a steric number of 3, you have an sp hybridized atom, okay? You have an sp2 hybridized atom, I'm sorry. If you have a steric number of 3, you have an sp2 hybridized atom. Why? Because you have 1, 2, 3 electron domains, right? This guy here is flat with 120 degrees. And that's why it is trigonoplanar, right? So that's actually still true also if you had that carbonyl carbon I keep on talking about right there. That's also trigonoplanar. Oops, let me draw that over here so you can see it better. The carbonyl carbon right here, right? Oxygen connected to carbon double bonded with 2 other bonds, right? This is also 120 degrees. I talked about that when I was talking about amoxicillin, the antibiotic, and why having that carbon there squeezed to 90 degrees makes it so unstable that it's a very good antibiotic, right? It's also flat. It's also 120 degrees, right? It's also sp2, right? So whether you're a carbon or you're a boron, these rules apply. Trigonoplanar, I don't know why I'm saying this again. Realize that the boron atom in boron trifluoride is sp2 hybridized, which you already knew that. The atom, the 3 bonds are made of sp2 orbitals, and the unhybridized p orbital remains empty. Oh, it remains empty because boron is 1 less than carbon on the periodic table, right? Has less electrons than carbon. Then we have the SPs, which are the linear ones, right? And we already knew before, right, that acetylene was linear. Remember that? And that was an SP. Same thing here with beryllium hydride, right? It's SP, 2, 1, 2 electron domains, right? with 180 degrees because it's a it's gonna, because it's linear, right? And we already said before also that the steric number of 2 means it's an sp, right? So even boron, comparing the carbon to the beryllium, same properties as far as sp hybridization and molecular geometry, right? It says draw a Lewis structure for carbon dioxide here, right? Are the p orbitals on carbon dioxide on carbon atom also empty in this compound, like they are with beryllium? In the previous example, well, let's just draw it real quick. Well, carbon dioxide is actually super easy, right? That's carbon dioxide. There are the lone pairs that go on to oxygen, right? And are the p orbitals empty? No, they're not, right? Because you actually have those p orbitals there coming together to make the double bond, right? To make the pi bond. Those p orbitals coming together. Those p orbitals coming together to make the pi bond, right? Between the carbon and the oxygen, right? Up here we have a single bond. Okay? So, just to I guess, bring it all together, okay? If you have a steric number of 4, you're sp3 hybridized. You are of tetrahedral arrangement when it comes to electron pairs, right? But if you have no lone pairs, you are tetrahedral when it comes to geometry. If you have one lone pair, you are trigonopyramidal. And if you have 2 lone pairs, you are bent. If your steric number is 3, then you are sp2 hybridized. That gives you a trigonoplanar arrangement of electron pairs. And if you have one lone pair, you're bent. If you have no lone pairs, you're trigonoplanar. Did I say trigonoplanar over here? I meant to say trigonobipyramidal. I apologize. Well, you can read it for yourself, right? I'm a little hard of English, you know, because I'm Asian. Anyway, so if you have a steric number of 2, that gives you an sp hybridized orbital. That gives you linear arrangement, and that also gives you a linear molecular geometry. So we have a lot more to go with this particular lecture when it comes to reviewing general chemistry, but I'm going to end it here because, I mean, we've gone for a long time here, and I think that's a lot of information for one day. So we're going to go ahead and end it here. But just know that there are no quizzes or assignments that are assigned today in lecture, but there will be some tomorrow, right? And then I'll see you in the next video later today for lab.